Today's lesson is on basic exponential functions, including growth and decay, and on how to use the fancy pens on Microsoft Whiteboard. So, in the previous video, we looked at exponential functions in a graph, in a table, and in an equation. So we're going to start there. So we know that the graph has this exponential increase or decrease, and that on the other end of the graph, on this part right here, we have an asymptote. So recognizing a graph is pretty easy. In the example that I'm going to use throughout this lesson, we're going to look at this table of values. So in this table, I can tell that it is increasing times 2 each time. So that's my rate of exponential growth. So I would expect my y value to go up times 2 every single time. So if I'm writing an equation for that, it would be in this form. So f of x equals a times b to the x power, where a is the y-intercept, b is the factor by which it's growing, and then x is the variable. So in this particular case, hang on, I thought I wrote this equation, but I must have done it lower on. In this particular case, my equation would be f of x equals 3, which is my beginning value from the table, times 2 to the x power. So again, here's my y-intercept, so that's going to be this value, and then here is my factor by which I'm going up each time, and that's going to be this value. So my basic equation is always going to be in that form, and we're going to keep coming back to that as we look at the at growth and decay, and then at geometric sequences tomorrow. So if we have that equation, more often than recognizing an exponential function on a graph, we actually have to graph it. So if we're graphing from this equation, I would recommend that you first find the y-intercept, which is going to be the a. So we know, I'm going to highlight that in the same color. Oops, nope, it didn't change colors, sorry. Up to green. So that's going to be 3 in this case. And then I'm going to make a table of values. So I know that it's going up exponentially, and I know it's going to have an asymptote, but I need a few more values before I can actually sketch the graph. So I would basically use my equation, I'm going to say if I'm graphing, I'm going to always use the y-intercept, and then I'm going to do at least a couple numbers on one side of the curve, and then maybe another one in the negative side to see what's happening to my graph. So again, if I'm using the original equation, if I plug 0 in, y is going to be 3. If I plug 1 in, y is going to be 6. If I plug 2 in, y is going to be 12. And if I plug -1 in, we've got 2 to the -1 power. So we have to remember what those negative exponents do. 2 to the -1 power is the same as 1/2, and 1/2 of 3 is 1.5. So then I can sketch my graph. So I'm going to go back up here to, trying to get it all in one frame for you. I'm going to go back up to the graph and plot those points. So I made, there was my 0, 3, there was my 1, 6, there was, I didn't do 2, 12 because it would have been way up there. There's my -1, 1.5, and I know it's getting closer and closer to the asymptote, so I have enough points now to draw my curve. So those are basic exponential functions, and that piece of it, again, we should try to be really comfortable with that. From there, what starts to cause some confusion is, what about when we're talking about growth and decay? So when we're looking at exponential functions and we're looking at real life situations, we often express them as a rate instead of as a factor. So Growth and decay functions are the same basic idea as a basic exponential function, but the factor by which we are multiplying is expressed as a percentage of growth or decay. So let's dig into what that means. So I'm going back to my basic example. This was the equation that I used up above. And I'm starting at 3. I'm multiplying it times a factor of 2 each time. So I'm calling this my factor. But in real life situations, we don't always say that it increases times 2. We would say instead of saying that it's multiplying times 2 each time, we would say that we have 100% growth. So the 100% growth means that starting with the 3, if I'm going to grow 100% each time, then I'm going to take that number times 100%. So, that number times 100% of that number. So times 2 is the same as saying if that 100% growth. I'm just expressing it as a percentage of growth instead of as a factor. So here's my times 2 each time, but I could also say that that's 100% of the previous value plus the previous value. So for example, if I'm going to start with 3, I've got 100% of 3, which is 3, plus the original 3, and that ends up being 200%. So I've got 100% of it right here, and then I've got 100% of the original amount. So that's where the 200% comes from, and we know that 200% is also just 2, which is going back to this factor that we used up here. So it's just a different way of writing it using a percent of growth instead of a factor. So I'm going to come back over here to this part. I can write it as my beginning value of 3 times 1 multiplied times itself plus 100% of itself, and then raising that to the x power. That 1 plus 100% is simply 2. Just another way of writing that factor. So this example is pretty easy because I'm using 100%, but let's look at another example where it's not 100%. So again, in real life situations, we often express it as a rate of growth. So I might start with $100 in the stock market. It's growing at 10% each year. So this 10% is my growth rate. But the 1 is 100% of the initial value. So I'm starting with 100 times 1. But I'm also multiplying it times 10% each time. So again, that's called my growth rate. So this really looks a lot the same, but it's written in a percent format. I don't like the way I just said that. Let me back up and just say it looks a lot the same. So again, 100 is my initial value. The 1 represents the 100%. The 10 represents the growth rate because 0.10 is the same as 10%. So I'm going to write that this is a 10% growth rate. Exponential decay is similar. So I'm starting with my initial value of 100, but when I'm decaying, it's getting smaller. So I'm decreasing, I'm subtracting, I'm subtracting 10% this time. And so I don't usually write it as 1 minus 0.10. I simplify that and write it as 0.9. So when I'm looking at an exponential function and I have a number here that is less than 1, I know that it's decay. It's getting smaller. Other than the fact that we're writing it and talking about that factor, that rate, as a percentage, basic exponential functions and growth and decay are exactly the same thing. So I'm going to stop there and give you a chance to practice some of that. Tomorrow we're going to do some interest problems that are real life examples of exponential growth, and we'll also look again at geometric sequences and how they really are very much like basic exponential functions.